Look at the screen you are staring at right now. We're going to unpack the absolute magic behind that glass in today's explainer, taking a deep dive into the truly fascinating evolution of screen technology. Because to actually understand how we got to the stunning paper-thin displays we use today, you have to realize that all of screen history is essentially defined by one fundamental, decades-long battle in physics.
Think about this for a second. You know, when you're watching a terrifying horror movie on a budget laptop or maybe an older TV, and the pitch-black shadows aren't, well, actually black. They're kind of this murky, glowing gray. Why exactly does that happen? Well, that annoying gray glow is the direct result of this massive technological war.
Okay, let's dive right into this. The entire landscape of display tech basically splits into two fundamental camps: light producers and light controllers. Light producers are displays where every single pixel literally generates its own glowing light. On the flip side, we have light controllers. These panels don't create any light of their own. Instead, they rely on a giant, always-on backlight, and the pixels just act like tiny, microscopic window blinds, opening and closing to let that light pass through.
To make sense of all the confusing acronyms you see at the electronics store, we're going to follow this battle through 5 quick chapters. The original producers, the era of the controllers taking over, the decades spent fixing the backlight, the triumphant return of OLED, and finally, the ultimate display future.
All right, kicking things off with Chapter 1, the original light producers, CRT and plasma.
Remember those massive, boxy screens from the 90s? The Cathode Ray Tube, or CRT. These things worked by actually firing a laser-like electron beam at a phosphor coating inside a glass tube. And because the phosphor produced its own light, they delivered true blacks, super rich colors, and absolutely zero lag. Gamers loved them. But they had some fatal physical flaws. They were ridiculously bulky. A standard monitor weighed a staggering 30 kilograms. Plus, they had a massive power draw, generated intense heat, and had this constant flickering that caused terrible eye strain. Manufacturers knew they needed a thinner solution, so enter plasma displays in 1995. Instead of a giant electron gun, engineers brilliantly turned every single pixel into its own miniature fluorescent lamp. When electricity hits the neon and xenon gas inside the pixel, it turns into plasma, emits invisible UV light, and excites the color phosphors. It was genius. It kept the incredible black levels and motion clarity of a light producer, but it inherited all the old problems. They were incredibly heavy, ran super hot, used a ton of electricity, and suffered from permanent screen burn-in. They were also just astronomically expensive to make. The industry desperately needed a cheaper alternative.
Which brings us to Chapter 2, the light controllers take over. To solve those flaws, engineers decided to completely abandon light-producing pixels.
This was the dawn of the liquid crystal display, or LCD. Remember our window blinds analogy? Here is exactly how it works. Step 1. At the back of the TV, a bright white backlight is permanently left on. Step 2. Sitting in front of that light are millions of microscopic liquid crystals. When you apply electricity, these crystals physically twist to either block the light or let it through. Step 3. The escaping light passes through red, green, and blue color filters to create your picture. Now, because LCDs only control light, they are unbelievably thin, incredibly cheap to make, and super energy efficient. But they have a fatal flaw. Those liquid crystal window blinds, they can never completely block out the backlight. And boom, that is exactly why you get those murky gray horror movie scenes.
Now, what's really interesting here is how manufacturers learned to tweak these microscopic window blinds for completely different audiences. Not all LCDs twist their crystals the same way. If you're a competitive gamer who needs pure speed, you want a TN panel. It twists incredibly fast for 1 millisecond response, but kind of washes out the colors. If you're a graphic designer, you want an IPS panel. Its crystals rotate sideways, giving you massive 178-degree viewing angles and highly accurate color. And if you're a movie lover, a VA panel offers the best compromise, with really deep blacks and high contrast, even though it can sometimes suffer from ghosting during fast motion.
Moving on to Chapter 3, fixing the backlight problem. Fun fact, if you've ever bought an LED TV, you actually just bought an LCD TV where they tried to patch that backlight flaw. Early LCDs used CCFLs, thick, toxic fluorescent tubes that were slow and power-hungry. Around 2008, they swapped those out for LEDs. Budget TVs used edge-lit LEDs around the borders, while premium ones used direct-lit LEDs right behind the screen. But to truly fix the whole gray-black problem, they invented local dimming. They divided the LED backlight into specific zones that could turn off independently. Eventually, they shrunk these lights down to create mini-LED, giving a single TV thousands of microscopic dimming zones for massive brightness and way better contrast.
But even with mini LED, we hit a physics wall, because one dimming zone still illuminates hundreds of pixels if you have a bright white object on a pure black background, like say a bright white ship in dark space. The light inevitably bleeds into the dark pixels. This creates what the industry calls blooming, which is just an ugly glowing halo. You literally cannot cheat physics when your backlight is separated from your color pixels.
And that makes Chapter 4 so incredibly exciting. The light producers finally returned to eliminate the backlight altogether.
This breakthrough was OLED, organic light-emitting diodes. Inside an OLED screen are organic compounds that emit their own light the exact millisecond electricity passes through them. Because there's zero backlight, every single red, green, and blue pixel can literally turn itself completely off. This gives you absolute perfect blacks, infinite contrast, and instant response times. They're basically millions of individual perfect lamps. The only major catch here, because the materials are organic, they do age, which introduces a risk of permanent burn-in if you leave a static image on the screen for way too long.
And this brilliantly illustrates the difference between our two camps when you're watching a really dark movie scene side by side. The OLED light producer literally turns its pixels entirely off. Bam, perfect black. Meanwhile, the LCD light controller has to keep its backlight firing, causing that light to bleed right through the crystal window blinds, giving you that frustrating blooming effect. Let's actually connect this right to the device sitting in your pocket. Your smartphone likely uses AMOLED, Active Matrix OLED. That simply means every individual pixel gets its own dedicated transistor, making the display incredibly fast, crazy sharp, and highly power efficient, which is great for saving your battery. Engineers even stepped it up a notch to Super AMOLED by removing the tiny air gap and building the touch layer directly into the screen itself. That makes your phone much brighter and totally readable even when the sun is glaring right at it. Finally, Chapter 5, the ultimate display future. How do we actually get the best of both worlds? First off, let's clear up some massive consumer confusion. QLED is not OLED. A QLED is honestly just a light-controlling LCD that uses a fancy layer of quantum dots to filter the backlight for better colors. It still suffers from blooming. However, a QD-OLED is a genuine breakthrough. It uses a pure blue OLED panel as its base, and then uses quantum dots to cleanly convert that blue light into red and green. So you get the perfect blacks of an OLED combined with the blinding brightness and pure colors of quantum dots. But if you want the absolute ultimate, flawless climax of display evolution, you want MicroLED. Imagine taking the perfect blacks, the infinite contrast, and the instant response of OLED, but completely stripping out the organic material. Instead, every single pixel is an actual, physical, microscopic LED. Zero burn-in risk, ridiculous brightness. It is literally the perfect light producer. The only hurdle? Perfectly manufacturing millions of tiny, microscopic LEDs without a single error is so intensely difficult right now that these screens are astronomically expensive.
Before we wrap, I have to mention the ultimate wildcard, e-ink. E-ink basically refuses to play the game entirely. It neither produces nor controls an internal backlight. Instead, it uses tiny capsules filled with black and white particles. Electric fields physically move these particles around to reflect the ambient light in your room, exactly like real paper. It is wonderfully easy on the eyes and uses almost zero battery, making it perfect for e-readers, even if the refresh rate is way too slow for watching a video.
So the absolutely crucial point here is this. The entire timeline of display technology is just a constant, relentless push for 4 goals: better images, lower power, thinner designs, and higher durability. Every single generation solves the weakness of the last. CRTs gave us instant images but were too heavy. LCDs made things thin but lost our true blacks. OLED brought the perfect blacks back, and MicroLED aims to make them last forever. So I want to leave you with this. Look very closely at the screen you're watching this explainer on right now. Based on the deepness of the blacks, the viewing angles, and the overall brightness, is your device a light producer or a light controller?